Hello. This will be a demonstration of Proposition 4 from Book 2 of Euclid's Elements, which states that if a straight line be cut at random, the square on the whole will equal the squares on the segments plus twice the rectangle contained by the segments. Again, as with all Book 2 enunciations, far from obvious without an example. So let's draw this example. We are given a straight line AB, like so. I'm gonna make that a little longer. Okay, awesome. And it is cut at random at point C. Now, we are saying that the square on AB, which is the whole, equals the squares on the segments being AC and CB. We're saying that the square on AB is equal to the square on AC plus the square on CB, plus twice the rectangle contained by the segments, that is, twice the rectangle contained by AC and CB. Okay, so first thing we ought to do, just construct everything. First thing we do, we make this square on AB. We shall call this square D, or square ADEB, and we construct it on the straight line AB by virtue of proposition 146. Now we join the straight line BD, simple postulate 1, and then we say that through C we draw the straight line CF. This chalk is ugly. We draw the straight line CF such that it is parallel to AD or BE. AD and BE are parallel to each other, and so you can make CF parallel to either and it'll be parallel to the other. We can do this by proposition 131, and similarly through point G being the intersection between BD and CF, we shall draw the straight line HK like so, such that it is parallel to either AB or DE, like that. And that is our construction. Now, because CF is parallel to AD, we made it that way, we can say that the angle CGB is equal to its corresponding angle ADB. This is proposition 129. There are three parts of it, but here we are using the second part. We also know that because AD and AB are equal, we know they're equal because they're two sides of a square. This is definition 122. We can also say that angle ADB is equal to angle ABD because of proposition 15. We notice that AB and AD are the two sides of an isosceles triangle, and so we can say that the angles which they subtend the angles on the base are also equal. Now, both CGB and ABD are equal to ADB, and so we can say that they're equal to each other by virtue of common notion 1. We can say that the angle CGB is equal to the angle CBG. Yeah, they're the same angle. And because these angles are equal, by the converse of 16, we can say that the sides which subtend them are also equal. In this case, that would be to say that CB is equal to GC. Now, we also know that because CK, we know that the figure CK is a parallelogram, and we know by virtue of proposition 134 that the opposite sides of a parallelogram are equal. And so the opposite side of CB is GK, and so those are equal. And the opposite side of CG is BK, and those are equal. And so now we have the parallelogram CK where all four sides are equal. We can do this by common notion 1. BC is equal to CG. CG is equal to BK, so BC is equal to BK. We also know that BC is equal to GK, and so we can say that BK is equal to GK. It's just a bunch of common notion 1 here. And so we can say that the parallelogram CF is equilateral. Now, we shall move on to describing the angles of this parallelogram. Now, we know that the straight lines CG and BK are parallel. They are parts, or they are segments, I should say, of CF and BE, which are parallel. We know this because we made them that way in the first step. We can say that the co-interior angles, that is KBC plus GCB, we can say that these two angles add up to two right angles. This is again proposition 129, a different part of it. This is the final third part of it. It's the same proposition. Now, we also know that the angle KBC being the angle ABE and ABE being in a square, we can say that the angle KBC is a right angle. We know that all the angles of a square are right angles. This is definition 122 again. And so this angle inside a square will be a right angle. And so because the angle KBC is a right angle, and it adds to another angle such that their sum is two right angles, we can use common notion 3, subtracting equals from equals, to say that the angle GCB is also a right angle. And likewise, because of proposition 134, we can also say that the opposite angles of a parallelogram are equal. And so we can say that the angle let's draw that out. We can say that the angle opposite to KBC, that is CGK, is also a right angle. And the angle opposite to GCB, that being CBK, or BKG, is a right angle. And so in the parallelogram CK, we have all the angles being right angles. We also know from step 3 that the parallelogram CK is also equilateral. And so a quadrilateral that is both equilateral, all the sides are equal, and right angled, all the angles are right angles, is a square. And so we can say that the whole parallelogram CK is a square. Now, CK is evidently on CB, and so we can say that the square CK is equal to the square on BC, square on CB. Okay, now similarly, that is using steps similar to 2 through 4, we can prove that the parallelogram HF is also a square. We can prove that it is both equilateral and right angled, and so is a square. And we also know that HG and AC, because of proposition 134, these opposite sides of a parallelogram AC and HG are equal, and so we can say that the square HF is the square on HG, and HG is equal to AC, and so by a property of magnitudes, we can substitute the side of a square for an equal length, and so we can say that the whole square, or not the whole square, just the square, HF is equal to the square on AC. They are contained by equal sides. Now, moving on to the two rectangles here, AG and GE, we know that these two rectangles must be equal. This is proposition 143. These are the complements of a parallelogram, and so these parallelograms, or these rectangles, are equal. And so, yes, the rectangle AG is equal to the rectangle GE by proposition 143. We also know by step 2, we proved that CB is equal to CG. And we can also see that the whole rectangle AG is contained both by AC and CG. And so we can say that the rectangle AG is equal to the rectangle contained by AC, a side by which it is actually contained, and CB, a side which is equal to its other containing side. This is again a property of magnitudes. We've seen this throughout all of book 2, where you can substitute containing sides out for their equals, and you will have equivalent rectangles. And so the rectangle AG being equal to the rectangle contained by AC and CB, we can also say that the rectangle AG plus the rectangle GE is equal to double the rectangle contained by AC and CB. This is common notion 2. We are adding equals to equals. We can say that the rectangle GE being equal to the rectangle AG is also equal to the rectangle contained by AC and CB. And so if you add AG and GE together, you'll get double of whatever their equals are because they're equal to the same thing. And so we can say that AG, the rectangle AG, plus the rectangle GE is equal to double the rectangle contained by AC and CB. Now, it is self-evident that the whole square AE is composed of the square HF, the square CK, the rectangle AG, and the rectangle GE. Right? So we have this whole square here, and it is composed of this square here, HF, this square here, CK, this rectangle, AG, and this rectangle, GE. This is self-evident. And so we can substitute all of these quadrilaterals, all of these squares and rectangles for their equals. What does that mean? Well, we know that the square AE is the square on the whole AB. We made it that way in step 1. And so that is the first thing we can substitute. We can say that the square on AB is equal to the square on AC, the square HF is equal to the square on AC, plus the square on BC, because the square CK is equal to the square on BC, plus twice the rectangle contained by AC and CB, because this double is equal to the rectangle AG plus GE. And so we can say finally that the square on AB equals the square on AC plus the square on CB plus double the rectangle contained by the segments AC and CB. And this being what was set out to have been proven, we are done with the proposition, therefore, etc. QED. Two things to note about this proposition. One is an unsaid porism that I find that Euclid uses decently often. And this unsaid porism is that the parallelograms about the diameter of a square are also squares. So when I talk about the parallelogram, or what I mean by the parallelograms about the diameter, are these right here. So whenever you have like a square like this, okay, this is its diameter, and the parallelograms about it are going to be these two areas right here. And from this proposition II.4, it is manifest that these areas right here, these parallelograms, are also squares. This Euclid will leverage to say that certain lines are equal because they are the sides of a square. So they are the sides of the squares about the parallelograms, about the diameter of a square. Gets all cluttered. So this is an unsaid porism, but it is very important to note that Euclid will use it. And again, I will, well, similarly, what we've seen with the other propositions of Book 2, this is algebraic geometry. Or at least that's how we would understand these propositions now. And so let's try and figure out what this proposition means in algebraic terms. Okay, so let's look at the diagram. So we have the whole straight line AB, but it will be more helpful to make our variables the segments. So I shall call the straight line AB A, and I shall call the straight line CB B. And so what we can see is that A plus B squared, the whole is A plus B. And so the square on that is just A plus B squared, equals the squares on the segments. Well, the segments are A and B, and so this is A squared plus B squared plus twice the rectangle contained by the segments. We've seen before that rectangles being contained is equivalent to multiplication. And so double the rectangle contained by the segments would look like 2AB. Now this, if again, you've ever taken a standard high school maths program, you will recognize the expansion of A plus B squared to be A squared plus 2AB plus B squared. And that is all I have to say about this proposition. So I'll be ending the video here, and I will move on to 2.5.